Okay, we've talked about function transformations, right? We've talked about vertical shifts, horizontal shifts, and reflections. Today we're going to talk about even and odd functions and the last ones. And the last ones are really special. Okay, you guys are going to love these last ones. Okay, so again, just a little reminder on what things look like. So we talked about vertical transformations. And vertical transformations, what we said is, well, if we have a function, I don't know, like the square root of x, and if we add a number on the outside of this function, what happened? It gets bumped up, right? And that was a vertical transformation. That square root function just pops up. It's like your mood. This is like your mood. If your mood is the square root of x, then this transformed function is what your mood looks like after math. Just bumps you up, all right? If we add a 2 on the inside, remember, inside is horizontal stuff. Outside is vertical. So if we add a 2 on the inside, it's a horizontal transformation. And remember, on the inside, it's also kind of backwards what you might expect. So we add a +2, it gets shifted over 2 units. All right? Move over. Social distancing, 6 feet, or something like that. I don't know. My metaphors aren't amazing. We also talked about other stuff. Talked about reflections. If we put a negative on the outside, again, outside, think vertically. If we put a negative on the outside, it flips it upside down. And if we put a negative on the inside is like horizontal, it flips it left to right. Reflections about the x or the y-axis. So that's where we're at so far. We're going to talk a little bit more about this. Specifically, what we're going to talk about today is with stuff like x squared, right? If I do a reflection about the x-axis, that flips it upside down. If I do a reflection about the y-axis, it flips it left to right. But notice, adding this negative, reflecting about the y-axis, doesn't change anything because it is already symmetric with respect to the y-axis. Symmetry is what we're going to start by talking about today, and even and odd functions. If you had to guess whether x squared was even or odd, hopefully you would guess even because, there's a 2. But that's what we're going to get into. And no, it's not sad that you understood this. If you understand a review, that means you are ready to get into the new stuff. You can be excited to learn and feel confident that your understanding is where it's at. Oh, my word. I'm trying to really up the level of cheese in this lecture today, I think. How cheesy can it get? Okay, so let's get learning. We're not going to start with this table. This table was a review. You should have this table as well. This table is very useful. We're going to fill in more of this table today. Okay, so what we're going to start with is I don't know where it went. What we're going to start with is a continuation of last time. This is what we did at the end of last time. We're going to talk about even and odd functions. All right. No. My confusion was I have just been misplacing all my papers today. So, definition. If these are going to be a double definition, 2 definitions, and each definition's got 2 parts. Okay? It's like a hamburger. Double the meat, double the cheese. I think that's what double means. I don't know. Those are big at In-N-Out, which apparently you don't have In-N-Outs in Wyoming. But I guess there's a lot of things that are not in Wyoming, I suppose. You know what there is, though? Snow. Right now, apparently. Okay, so if f of x equals f of negative x, then f is even. And here's the double part. Its graph is symmetric with respect to, I'm never writing that again. A lot of times I'll abbreviate that WRT. With respect to the y-axis. So there's two ways of checking whether something's even or odd. Right? This is a double definition. If plugging in a negative number is the same as plugging in a positive number, then it's even. But say you don't like algebra, God forbid, then you can also check whether the graph is symmetric with respect to the y-axis. All right? Essentially, right, we know what this right-hand side looks like. Right? The right-hand side, we talked about that. This right-hand side is a horizontal reflection about the y-axis. So if this reflection doesn't change anything, then it's an even function. Just like this, right? We reflected this function, and it didn't change. That's how we know it's even. Or you could say, well, Jason, I know that's even because look at this graph. It's symmetric about the y-axis, right? On the right side of the y-axis, on the left side of the y-axis, it's just reflected, okay? Symmetry. That's why it looks so beautiful. That's why quadratics are just such beautiful things. So, now there's a very similar, but not similar. It's not really that similar of a definition. That's the first definition. Little number one. We got a second definition, the second part of the double-double. If f of x equals negative f of negative x, right? And then f is odd. I don't have to write the whole thing. And its graph is symmetric with respect to the x-axis. So remember, I use these squiggles sometimes when I'm writing the same things that I wrote above, and I just say, well, that's redundant to write it again. We already wrote it. So we have a very similar but sort of different definition here. So let's unpack this, okay? Over here we said, what is this right-hand side? This right-hand side is a reflection about the y-axis. Well, this right-hand side for odd functions is also a reflection about the y-axis, but it's got another negative right here, a reflection about the x-axis. So this one says, if you reflect it around both axes and get the same thing, then it's an odd function. So let's try to find some odd functions. Let's look at our toolkit functions. So this one is not going to be an odd function, right? Reflected around one axis and reflected around the other axis. Oh, that's not the same thing. So x squared is not an odd function. Let's look at some others, some other ones. If we have a square root function, let's see if that's an odd function. Well, if you reflect it around one axis and then reflect it around the other axis, does the orange and the blue line up? No, they're different. This is not an odd function. Odd function means if you reflect it on both axes, then you get the same thing. Okay? Okay. So let's keep discovering odd functions. All right, let's maybe this is an odd function. Maybe the absolute value of x is an odd function. Who knows? Let's reflect it around the x-axis. Oh, wait. Sorry, y-axis. When we reflected this around the y-axis, nothing changed. This one's actually an even function, right? It's symmetric with respect to the y-axis. Same on the right as it is on the left. Your directions are backwards from mine. Same as the right as it is on the left. But if we reflect it upside down, it's not the same. Right? If we reflect it both times and get the same function, it's odd. All right, what about x cubed? Well, first, let's reflect x cubed about the y-axis. And then let's reflect x cubed about the x-axis. Aha! Notice how these are the same functions. The graphs are right on top of each other. So this is an odd function. Reflect it both ways, get back the same thing. That's what an odd function means. All right, let's do one more. All right. Cubed root of x. Reflect it about the y-axis. Reflect it about the x-axis. Here we go. Another odd function. All right. So that's kind of what's going on with even and odd functions. So let's unpack this a little bit, shall we? Let's do example 11. Wow, so many fun examples in this section. How lucky we are to be able to. Keyboard, if you don't stay put, I'm going to have it talking with you after this. All right, example 11. Square root of x was actually neither. And let me show that real quick. So if we reflect it around the y-axis, these have to be the same for it to be even. And it's not. And then do the other reflection, these would have to be the same for it to be odd. So that's actually a good point, Delaney, that I should have brought up. Because with numbers, all integers are either even or odd. But for functions, you can have an even function, an odd function, or just a neither function. So it is possible for it to not be even or odd. And I guess that works with numbers too, right? Integers are even or odd, 1, 2, 3, 4, 5, but not all numbers are even or odd, right? If I ask you, is 2.63 an even number or an odd number? Say 2.63, that's not even or odd, you weirdo. Why are you asking me that? It's the same thing with functions, okay? All right, so example 11. Is f of x equaling x cubed plus 2x even, odd, or neither? So we're going to check this with the definitions, and we'll verify it with the graph. Okay? So what was the definition? I don't even remember. There were two definitions, right? Even, I was lying to you, I do remember. Even means its graph is symmetric with respect to the y-axis, like a parabola, x squared. The way we check it is we see, is f of x equal to f of negative x? So you need these definitions. So let's check even first. Is f of x equal to f of negative x? Because even means symmetric about the y-axis. So is it the same on the left as it is on the right? So let's look at f of negative x. Oh, wait a minute. This is like function composition again. Whoa! Function composition, never letting go. Function composition, by the way, is not on your quiz tomorrow. That was on your exam on Thursday. This is on your quiz tomorrow, okay? So we plug in, we look at f of x. Everywhere that there's an x, we replace with a negative x with parentheses. So we got negative x cubed plus 2 times negative x. Let's simplify this. You're going to have to simplify this. Simplify. So if you cube negative x, it becomes negative x cubed. If you squared negative x, it would become a positive. But because there's an odd exponent, it stays negative. And then 2 times negative x is minus 2x. So is this the same? These are not the same. They're opposites. That'll come into play when we check whether it's an odd function. So it's not even. Not even. Angry face. I have this class to thank, by the way, for my high quality angry faces. All right, so let's check odd. We need to look at negative f of negative x. Well, we already found what f of negative x was, right? This is f of negative x. So negative, right? Because this already is f of negative x. We don't need to do that calculation again. You could if you wanted to, though. And now we just distribute that negative. Negative times a negative is a positive. We get x cubed. Negative times a negative is a positive. We get plus 2x. Oh. That is the same thing, isn't it? X cubed plus 2x, x cubed plus 2x. That is equal to f of x. Oh, I should have said this is not equal to f of x. This is equal to f of x, so it is odd. Giant happy face with happy eyebrows. So it's not even, it is odd. And that's how we do it. Okay? So you just check it. Or you can graph it if you remember we need to worry about symmetry. Right? Hold on, this is not right. I gave you an incorrect definition over here. I got a little carried away. I apologize. For symmetry, right, it has to be symmetric with respect to, essentially, if you flip it around both axes. What do I have in my notes? Do I have this in my notes? It doesn't matter. I'll check that later. Its graph is symmetric. I apologize. This is actually pretty bad. So this is the definition for an odd function, but it's not symmetric with respect to the x-axis. It's symmetric with respect to the origin. Okay. So real quick, I kind of have to backtrack here because, yeah, I apologize, Monet. Let's go back and look at one of the odd functions we were talking about. So right, it's not symmetric with respect to the x-axis, but it is symmetric with respect to the origin. What that means is if I reflect this blue point, right, let's do this blue point. If I reflect this blue point about the y point, what's on the other side of the y point? It's still on the function. Okay. Any point you find, if you reflect it around the origin, the white point, it will still be on the graph. Okay. My apologies for giving you an incorrect definition. So let's check our answer for example 11. Okay. X cubed plus 2x was the function. Is this the same? Right? It's the same idea, right? If you reflect this point, you're still on the graph. Reflected about the origin right here. That's what odd functions look like. Also, as a little cheat, I'll make up for it, not by a second wig. You have to have patience for the wigs. I'll give you a little cheat here. If the function is a polynomial, so like x squareds, x cubed, x to the fourths, stuff like that. If all the exponents, that's not how you spell exponents, if all the exponents are odd, it's odd. If all even, then even. And if it's a mix, then neither. So if it's a polynomial, you can just look at the exponents. So that's why x cubed is odd, and why x cubed plus 2x is also odd, right? This is like an exponent of 1, right? If you wanted to think about it that way. But if I added an even exponent, now this is not odd or even. This is not symmetric with respect to the y-axis, right? It's not symmetric about here, so it's not even. And it's certainly not symmetric with respect to the origin, so it's not odd either. But if, we do some other polynomial like x to the fourth minus x squared, this one is even, right? Both of the exponents are even. And indeed, it is the same to the left and the right of this axis. We look at another polynomial with only odd exponents. Again, this is symmetric about the origin. Everything is symmetric about this white point. All right? So that's kind of even and odd. Any questions before we go on to the most interesting part of the section? Also, this is a good time for attendance. For the attendance question today, send me the name of a piece of furniture. Okay? If you have questions, ask them. For attendance, send me the name of a piece of furniture. I will go get a wig today. Oh, you don't want to hear my British accent. All right. All right, you guys ready? We're going to finish the section. We've got quite a bit more to go today. Also, I hope you love my curly hair, because this is actually what my hair kind of used to look like. It was kind of similar to this. Different color, obviously. Okay. Also, it looks like it's backwards. I don't know. Let's move on. We're going to start talking about vertical stretching and compressing. All right? So let's look at a square root function. Okay? Let's look at a square root function. Y equals the square root of x. You get one of these every week, and they only get more interesting. I have a mullet wig, but I couldn't style it right. So you don't get a mullet today. Okay? So, vertical stretching. You hear the word vertical. You hear the word vertical, you think outside the function, right? Just like vertical shift is adding something outside the function. Horizontal shift is something inside the function. Okay? So vertical stretching, well, if vertical shift is addition, vertical stretching is multiplication. Look at that. If we multiply the outside of the function by 2, it gets stretched. It goes, all right? Let's see them side by side. Multiply the outside of the function by 2. The blue turns into orange. We're just stretching it vertically. All right? And again, we could stretch it as much as we want. Stretch it by 3, by 4, by 5, by 6. Just takes all the y values and multiplies them by 6. And compression, right? What if I multiplied it by 1/2? If I multiply it by 1/2, then all the y values get halved. The y values get squished. It's a very awkward angle for my wrist. All right, so that's what vertical stretching and compression looks like. Just, it's on the outside, it's multiplication. It either stretches it to be bigger or compresses it to be smaller, all right? So, go back to your notes. And I luckily remember where these are. And we have to fill this in. New thing, vertical stretching, vertical stretch, and vertical compression. So vertical stretch was y equals a times f of x. Remember, vertical is always on the outside. We're multiplying the outside of the function. But here, a has to be bigger than 1. And compression is the same thing, right? Y equals a f of x, but this time it's a small fraction, right? Where a is less than 1. I'm going to say a is less than 1, but it's still bigger than 0. Otherwise, it's not technically correct. So some examples, right? Vertical stretch was like y equals 2 square root of x. An example of vertical compression was like y equals 1/2 square root of x, all right? So this table's almost filled. We only have the horizontal stretching and compressing after that. But don't worry, be patient, slow down. If you stress too much, your hair falls out. So let's use these. Stretching and compression. Ah, I was looking for this earlier. We found it. Great. Well, we use that after this. All right, let's go on to example 12. I should bring one of these bad boys out to college, like in the fall, if hopefully we're back in the fall. Just like show up right here. Yeah, I grew my hair out over the summer. No big deal. My hair grows pretty fast. It's the wrong color, but I have done weirder things. Remind me, for those of you who weren't in my class last semester, remind me to tell you about my awesome tattoo idea. Okay? Not today, though. Some other day. So let's say we have P of t, a function, and it models a population. I can't tell you now because it's about giving you a little taste. Leave you something to want so you come back for more. Give you a reason outside of extra credit and the knowledge and love of mathematics to come back to a math lecture. If you remember tomorrow to ask about it, I'll tell you. So P of t is going to be some function that models a population of fruit flies, very commonly used for experiments in biology. Okay? And I'm going to ask you something about Q of t. I see Gabe remembers. Bella remembers. All right. The question is, graph Q of t for a population with double the flies. So this is a vertical stretching. Okay? This is a vertical stretch because the y values, right? The y values are, in this case, the p values. The population is getting doubled. So in this problem, right, I give you the graph. Okay, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. I'll give you this graph, and just like before, you have to graph the doubled population. So P of t, the normal population, starts off at 0, 1 and goes to 3, 3. In what looks kind of like exponential growth. We'll talk about exponential growth later. And then something happens to the population, and it linearly decays to the point 6, 1. And then it really decays, and they all die. All right. So this is P of t. So the question is, you need to graph Q of t, which is double the population. Again, so Q is double. Right, that's a vertical stretching. So we just stretch all those y values by 2. I forgot how uncomfortable wigs are. So what's the y value here? The y value is 1, double it. Y value becomes 2. What's the y value here? It's 3, double it. Double 3 is 6. What's the y value here? It's 1, double it. Goes to 2. What's the y value here? 0, double it. 2 times 0, that's still 0. And then just use the same basic shape, exponential, linear decay, and more linear decay. And this is going to be our Q of t. All right, so that's how you do these sorts of problems. Vertical stretching and compression changes the y values. Oh, hello, cat. Good morning. I think I woke him up when I got the wig. If you're lucky, he'll stick around and you can see the other cat. But we've got math to talk about. He's screaming at me though. All right, let's move on. Next example problem. Where am I putting old notes? Right there, sure. Example 12, 13. We were counting too high today. Example 13. You remember this old friend, don't you? Fill in the table. We're going to name this table. Let's name the table fill. Okay. Here's a column, a row for x. We're going to have a row for f of x and a row for 1/2 f of x. The x coordinates, just like before, are 2, 4, 6, 8. Good old Phil. We remember Phil from Wednesday. And the y coordinates, or f of x, are 1, 3, 7, 11. Also, my cat says hi. Just chilling on the windowsill. So this is what kind of thing is here? Well, we're multiplying on the outside, so it's got to be vertical. And it's a smaller number than 1, so it's a compression. This is a vertical compression. Everything's getting halved. All right? So we have the y value. Yeah, good, Delaney. We have the y value, so it becomes 1/2. Have the y value, 3/2. Have the y value, 7/2. Have the y value, 11/2. Okay? Just another way to view these problems. All right. Now, we're going to make things a little bit more interesting with example 14. More graphing. Graphing really is where this section gets hard. So the graph G is transformed. I can't write letters today. It's transformed from f of x equals x cubed. Relate f to g and find its formula. So again, g is going to be given to you. And the question is, you need to find out what's going on. What function transformations are happening to this g? And I will give you the graph. Okay? So it has the point 0, 0, has the point 1, 1/4. That's point 1, 1/4. -1, -1/4. Has the point 2, 2. And then that's -2, 2 as well. So, how can you recognize function transformations? So, to recognize function transformations, we first have to be familiar with the basic graph, with the toolkit functions. This section will become way easier if you're familiar with toolkit functions. All right, so you need to remember what x cubed looks like. So let's make a table of some x's and y's of x cubed. Right? For example, when x is 0, x cubed is 0. When x is 1, 1 cubed is 1. When x is 2, 2 cubed is 8. And we have to see what's happening that this is our graph instead of this. Something has changed with g, right? This is f over here. Well, we don't have 1, 1, we have 1 1/4. We don't have 2, 8, we have 2 and 2. The y values are all smaller than we expected. But it's not a vertical shift, right? It hasn't just been moved. It's been squished. And the question is, how has it been squished? Okay. And the answer is, well, we thought we'd be at 1, a y value of 1 here, but we're actually at 1/4. A quarter of what we thought we were going to be. We thought at 2 we'd be at 8, but we're actually at 2. 2 is 1/4 of 8, right? 1/4 is 1/4 times 1, right? 2 is 1/4 times 8. So we're always, g is always 1/4 of what f is going to be. And that's how we, what is going on with this pen? That is how we recognize that we are getting vertically compressed. So, y values, compressed by 1/4. We're getting 1/4 sized. Got like some orange peel on my nail. So what we're going to do is we say, okay, so g of x then is 1/4 of f of x. And f of x is x cubed, so g of x is 1/4 x cubed. And that's our answer here. Okay? That's how we do this sort of problem. Any questions so far? Before we get into horizontal compression. You're confused, okay? Where did I lose you, Gabe? I'm assuming example 14, but maybe earlier. Okay, so let's go back to what we were asked first. We were asked to say, okay, how does g relate to our standard toolkit function x cubed? This was given to us. This graph was part of the problem. And we needed to know how this relates to x cubed. So what I said is, let's think about what x cubed looks like. So I made a little table for x cubed to see how it differs from g. So I just plugged in some points here to look at how the y values differed from these y values. The table is optional, but it's a really good idea if you're not super familiar with toolkit functions. So I just plugged in some values of x. If x is 0, 0 cubed is 0. If x is 1, 1 cubed is 1. If x is 2, 2 cubed is 8. This right here is the toolkit function. So then we compared our toolkit function with the given g. And then we said, oh, okay, look at this point right here, 1 comma 1/4. 1 comma 1/4 is the transformed version. 1 comma 1 is the untransformed version. So we looked at the relationship between a fourth and 1. Looked at another point, 2 comma 2. In the untransformed version, it was 2 comma 8. So we related the y values 2 and 8, which is what this came from. Okay, does that help at all? Or do you have further questions? Or anyone else have any other questions? Okay, good. Thank you for asking the question. Don't worry about this. This is old. This is old news. Hope you like that sound because I did it for an extra long time. Here's what we're going to do. We have 3 more examples. They're going to be tough. Well, some of them are going to be tough. Let's introduce horizontal stretching, compression real quick, and then we're going to put it all together. Okay. So let's go. Let's look at a parabola this time. Another toolkit function. So again, outside means vertical. Inside means horizontal. So if we had a 2 on the outside multiplied, right, that's vertical stretching. A 2 on the inside is horizontal. You might think a 2 on the inside is horizontal stretching. But remember that inside is always kind of backwards what you might think, right? If we plus a 2, that's not right. The orange graph got moved left 2. Whenever things are on the inside, they're always kind of flipped from what you might think. So similarly, if we multiply a 2 on the inside, it's not going to be a horizontal stretching. We multiply by a 2 on the inside, it's going to be a horizontal compression. Okay? So for horizontal stretching and compressing, it's on the inside. Inside is horizontal. But it's kind of backwards what you might think. This compresses it by 2 or a half horizontally. Okay? Goodness gracious. He is losing his mind. So let's fill in our table. We are finishing the table. All right? Horizontal stretch. And compress. So it's almost the same, but now it's what happens if we multiply it on the inside. And it's a stretch. Again, it's opposite what you might think if A is small. It's a compress if A is big. Opposite from the vertical situation. Just like with vertical shifts and horizontal shifts, it was opposite between those two things as well. All right, so an example of a horizontal stretch would be y equals 1/2 x squared. It's on the inside of the function. And an example of compress would be y equals 2x squared. And this is the one we did on the, I was going to say on the board, on the screen, on Desmos. So now you got a whole table of transformations. And these are, I'm pretty sure that this section is the single most useful section for if you're taking future math classes. Okay, we use transformations everywhere. And once you understand transformations, you understand so much more stuff about graphing and how it works, what graphs look like, what functions are going to look like, how things are going to behave. And getting that visual picture of how things work is really helpful for a future in math classes, all right, and other sciences as well. Okay, so this section is important, which is why we're spending so much time on it. It's a tough section. It's a long section. Your homework's going to take a long time. Even if you got above an 80% on the last exam, and a lot of people did get it above an 80%, please do the homework problems. These are good problems. They will be helpful for you in your future math stuff. We are going to be using this section, which we're not done, by the way. I'm just going off on a tangent. We are going to be using this section for the whole rest of the semester. Very commonly, when we talk about future sections, I'll be like, and yes, this is a function transformation, and we will need you to be good with function transformation. So this is, I think, the single most important section of the class. Okay, so it's important. So let's go on. Sorry, just having some itchy head problems. Let's do another problem. Let's do example 14. Right, and say, no, let's do example 13. What? Let's go back to the fruit flies. Okay. Go back to the fruit flies. And this time, do a horizontal compression. By 2. And whether you say by 2 or a half, I'll accept either one of these languages. All right. Also, I would like the class to really just notice what Delaney said. Delaney says she does not want me to be wearing a wig. So you might have to fight her if you want any more wigs in the future. So, not my words, or her words. But here we go. So I'm going to copy down the fruit fly picture from before. All right, this is 1, 2, 3, 4, 5, 6, 7. This is 1, 2, 3, 4, 5, 6. All right. Come on, Lexi, it was close enough. There's the underlying meaning, right? All right. So we started at the point 0, 1. We went to the point 3, 3. And then we ended at the point, then we had 6, 1 again, and semi, 0 is what we did. Started off exponential, then went linear, and then went linear again. How do we do a horizontal compression over here? Monet, because she said she can't take me serious with the wig, and math is serious business, okay? We need everything to be super serious over here, which is why I'm wearing a button-down shirt, because it's very formal, all right? So we need to do a horizontal compression by 2. Vertical, remember, changes the y values. Horizontal changes the x values. So all we do is take all of our x values and half them. So here, what's the x value at this point? It's 0. Well, half of 0 is 0, so this point doesn't change. Here, the x value is 3. We need to half it. So the x value becomes 1.5. Here, the x value is 6. We need to half it. The x value becomes 3. And here, the x value is 7. We need to half the x value. Half of 7 is 3.5. So this becomes our new graph. This red one, It's kind of small. I should have drawn it bigger. Horizontal compression just means everything happens twice as fast. So this, if we're actually thinking about a population of fruit flies, in the first example with vertical stretching, that's like if we had double the population. In this example, this is a horizontal compression. This is as if everything's happening twice as fast. So instead of the black thing, where the experiment took 7 days for them all to die, this is twice as fast. It took 3.5 days for all the fruit flies to die. Okay. All right. Any questions before we really just throw in everything together? We've talked about vertical shifts, horizontal shifts. We've talked about reflections. We've talked about vertical stretching, horizontal compressing, vertical compressing. We've talked about it all. Now we have to combine everything together. And this is where we finish the section. We got 3 problems to do. Okay? And then we'll be done. We're not going to start the next section today. So let's finish strong. Example 15 after a little note. So we're going to combine it all. Exclamation point, happy face. This happy face looks like passive aggressive or something. Oh dear. Anyway, so the order matters. So I will give you what order it is usually best to do things in. There are exceptions to this rule that you could do if you wanted to, but you don't have to. I think it's easiest to stick with this rule. Okay? So, do a horizontal shifts first. Shifts, that's not how you spell first. That's not how you spell first either. I can't spell today. The horizontal shifts first. And then take care of all of your reflecting and stretching. And then end with a vertical shift. So the only thing that matters is that horizontal shift is first and vertical is last. Everything else you can do in the middle, in any order. Okay? Horizontal shift first, left to right, then everything else, and then vertical shift up and down. If there's multiple function transformations, this is the order that you're going to want to do them in. All right? So, let us finish. I'm out of lettuce. I need to get some more lettuce. Example 16. Whoa. Fill in the table. For g of x is equal to 2 times f of 3x plus 1. And do it in steps, just like we talked about. Wait, we're on example 15? Really? Here, I'll fix this. Thank you for catching this, Monet. There we go. Now we're on example 16. Okay. We're gonna, hey, microphone, be gentle. All right, example 16 now. Fill in the table. We've got x, we've got f of x, and then we've got a couple more things. So x, this is gonna be something different. 6, 12, 18, and 24 are our values of x. I'm realizing I set this up not in a great way. F of x is going to be 10, 14, 15, and 17. And we need to make a corresponding table for everything else. So we're going to do it in steps. And remember what the steps are, right? The steps are horizontal shifts first. There are no horizontal shifts here, right? This is a horizontal compression, a vertical stretching, and a vertical shifting. So the first step, we're not doing. Second step, do the reflecting and the stretching. Okay. So we're going to start with the horizontal compression. Right? We're doing things one step at a time. There's 3 things going on here. We're just going to do them one at a time. So, right, this is a horizontal compression by 3. Just like we did in the previous example. In the previous example, right, we did a horizontal compression by 2, which means we halved all the x values. So we need to do the same thing here. But now it's a compression by 3. We need to thirdifies all the x values. So the y values aren't changing. It's still 10, 14, 15, 17. But we're compressing horizontally. All the x values get compressed by 3. 6 divided by 3 is 2. 12 divided by 3 is 4. 18 divided by 3, 6. 24 divided by 3, 8. We have done one function transformation. Okay. Let's do a next one. Again, what was our order? Horizontal shifts first? We didn't do that. Or we didn't have any of those. Reflecting and stretching. We need to do all the reflecting and stretching possible. So we did the horizontal compression. Now we need to do the vertical stretching. So the next row in our column has to be the vertical. We can't do this one yet. This is a vertical shift. That's got to be last. Vertical shifts always last. So we're going to do the vertical stretching. Let's look at 2 times f of 3x. So this is a vertical stretch by 2. So vertical stretch means all the y values get doubled. So 10 gets doubled to become 20. 14 gets doubled to become 28. 15 gets doubled to become 30. 17 gets doubled to become 34. All right, and the last function transformation is this vertical shift. So to actually get our g of x, we add a 1 plus 1. So there's a vertical shift up 1. That's not ap. That's an up. That's a u. So just bump all these things up 1. 20 bumps up to 21. 28 bumps up to 29. 30 bumps up to 31. And we started with x and f of x. We ended with x and g of x by doing all the function transformations one at a time. And this right here, 16 and 17, are going to be the hardest parts of the section. Okay, any questions on this before we do the last 2 graphing problems? Okay, let's finish off. Example 17. Given f of x, graph g of x on the same axes. All right, and for part A, f of x is going to be just x squared, a parabola. Might not have enough room here. All right, so 1, 2, 3, 4, 5. As a side note, if you do have graphing paper, it's a lot better to use graphing paper. I am specifically not using graphing paper just in case you also don't have graphing paper. Otherwise, it sort of gives me an advantage. All right, we'll go 10 in every direction. So x squared. This is a parabola, right? Any x coordinate you pick, the y coordinate is just that number squared. So when x is 1, y is 1 squared, which is 1. When x is 2, y is 2 squared, which is 4. When x is 3, y is 3 squared, which is 9. You can make a table for this if you wanted to. And then it's an even function, which means it's symmetric about the y-axis, which means the points will be the same on the left. And this is f of x. And what you need to do is graph g of x, which is going to be negative 2 times f of negative x plus 1 plus 1. So, tons of function transformations here. A lot of function transformations. We're trying to bring it all together right now. Okay? So, what we're going to do is just do them one at a time in the right order. Okay? So what's the order? Order is first do the horizontal shift. Okay? So the first thing we're going to do is take care of this horizontal shift. We're adding a plus 1 on the inside, which means it goes to the left 1 unit. All right? So, what do we have? We're just going to make a table just like we did in the previous example. Right? Make a table of our x's. And then what does f of x plus 1 look like? So this is left 1, right? So we just take all these points and move them left 1. We move the x values to the left. So what's this point over here? Negative 3, 9. If we move that left, it becomes negative 4, 9. Look at this point. That's negative 2, 4. We move it to the left, it becomes negative 3, 4. Negative 1, 1. Move to the left, becomes negative 2, 1. 0, 0. Move to the left, negative 1, 0. 1, 1, move to the left, becomes 0, 1. 2, 4 to the left is 1, 4. 3, 9 becomes 2, 9. So again, we're just taking all the points from our toolkit function and moving them left 1 unit. So the x-coordinate just gets bumped over, but the y-coordinates are all the same as our toolkit function. So, what's the next transformation we do? We consult our orders. It says do the horizontal shift first, and then all the reflecting and stretching. So it's your choice what order you want to do the reflecting and stretching in. I like to start with horizontal stuff. So next, let's do another table where we take care of this negative, this horizontal reflecting. So we have f of negative x plus 1. I should have done this problem on the second page. Right, this is a horizontal reflection. It reflects it about the about the y-axis. Okay. So again, this is reflecting about the y-axis. All the y values are staying the same. We can just copy all these y values down. The only thing that happens is the x's are getting flipped from negative 4 to positive 4, from negative 3 to positive 3. We just change the sign of all the x coordinates because now we have a negative x. right? This is a reflect in our second table. And we just keep on doing this. Yeah, Belle, you have a question? Thanks, Gabe. I was going to keep on going on the second side of this paper, but it really doesn't work. This right here, it's hard to see. But what it is f of negative x plus 1. Every table we write, we add another function transformation. And it's the negative next to the x that reflects it about the y-axis. Good questions. Thank you. So we have other reflections that we need, or other things we need to take care of. We also have a vertical reflection and a vertical stretching. And if you want, you could do these at the same time. So I want to write this next to it, but I'm out of paper. I'm just going to use a new paper and just keep going. So let's utilize the negative 2. All right, negative 2, f of negative x plus 1, is the next step. So we already had the f part, and now we're putting in the negative 2. This just changes all of our y values. This is a reflection upside down, turns all the y values negative, and it stretches all the y values by 2. So here the x coordinates don't change because it's only vertical stuff that we're doing in this step. We can copy down those same x coordinates. The y coordinates get all multiplied by negative 2. So we get negative 18, negative 8, negative 2, 0, negative 2, negative 8, negative 18. We just took all of these y values and multiplied them by negative 2. All right, this is a reflection and a vertical stretching. So we're just combining everything together, and it's complicated. But if we just do it one step at a time, it's not that bad. Well, it's still kind of bad, but not as bad as it could be. So the last thing, remember, going back to your order, first we did the horizontal shifts, and then we did the reflecting and the stretching. Only thing that's left is that vertical shift. So that's the last thing we do always. So last thing we do is a vertical shift. And again, we can use the same x values if we want to combine it here. The vertical shift is negative 2, f of negative x plus 1, plus 1. All right, this is a vertical shift of just up 1. So we just move all these points up 1. Negative 18 becomes negative 17. Negative 8 becomes negative 7. Negative 1 from negative 2. Just adding 1 to all of these values. And we finally have all the points to use for this graph. This new transformed graph. We threw literally almost every single transformed function at the same time at you. If you can understand this example somehow, you can understand the whole section. If you don't understand this example, that's fine, because we're literally using everything. So if you don't understand this example, what that means is that you don't have a mastery over the entire section. And if you did somehow have a mastery of the entire section, I would be surprised, right? I don't expect anyone to just know everything by the time we get to the end. But this is just to show you what it's going to look like when you get there. Okay? So this is G right here. This is our G of X. Right? G of X was negative 2. We did all these transformations one at a time. We finally got to our final X coordinates and our G values. So now what we do is we now plot those on the same graph. Trying to see the best way to do that. Maybe like this. Okay? Plot all the X coordinates. plot all the g coordinates, right? This is g right here. So we do it one at a time. 4, comma, negative 17. That's not going to be on. That's not going to fit. Skip to the next one. When x is 3, g is negative 7. So we plot the point 3, negative 7. When x is 2, g is negative 1. So plot the point 2, negative 1. When x is 1, g is 1. So plot the point 1, comma 1. Hey, we got a little buddy, the black and the red one. And then again, the next point is 0, negative 1. And then the last point, or the next point is negative 1, negative 7. And then again, we're going to have a y coordinate of negative 17, which is not going to fit. So we just plotted the x coordinate and the g values. And whenever you do function transformations, this red graph should always look kind of like the black graph. So if the black graph's a parabola, the transformed thing should still be a parabola. And so you can see the shape of it. It's upside down now and kind of moved around and stretched and shifted over. And we did a whole bunch of things with this. But that's our final answer. Okay? So again, I recommend doing the homework. If you're doing the homework and you look at a problem and go, I can't for the life of me see what to do with my notes from this. Send me a message, send me an email, send me a Discord message, okay? If you want to schedule a call, if office hours don't work and you want to get on voice call with me and talk it over, we can talk it over, okay? I don't expect anyone to learn this stuff by yourself. If you were learning it all by yourself, you wouldn't be taking a class, you just do it, okay? So I am here to help you if you have questions. So please ask them as they come, okay? This is a tough section. It's an important section. And yeah, we'll get through it together. Also, talk to your fellow students as well. Work together. Ask them questions as well. Utilizing the question channel in the Discord can be useful. That way you can all discuss things together, or I can answer questions if you want. You can also send it to me one-on-one if you prefer to do it that way. I prefer the Discord channel so that everyone can see it and everyone can benefit from it, but it doesn't have to be that way. Anyway, good luck. You have a quiz tomorrow on this material. Are you going to get something like example 17 on the quiz? Probably not. But I might give you a lighter version of this because this really is pretty heavy. Okay? If this makes you want to cry, then you're not alone. This makes a lot of people want to cry, Gabe. All right. Anyway, have a good day. Bye-bye.